Hello everyone, good day. My name is Ray Benting Flores and welcome back to my YouTube channel. So in my previous video about related rates, I have already informed you that I will be uploading more videos about or solving related rates problem. Last video, I have discussed the related rates problem involving ladder, and for today we will be discuss about related rates problem involving balloon. But if you don't have yet done watching my video about related rates problem involving ladder, the link is on the description box below. So in this video, we will be tackle or presenting some examples involved or solving related rates problems which is related to balloon, and we have these objectives the same from the last video, which is to the learner should be able to solve related rates problems and be able to illustrate a given word problems and into a mathematical sentence. So the first example is a balloon is rising from the ground at 140 feet per minute. Is struck by a rangefinder at a point A located 500 feet from the point of lift-off. Find the rate of which the angle at A and the range R are changing when the balloon is 500 feet above the ground. So in this given example, we are looking for two possible answers, which is the rate of change or the rate which the angle at A, and the range or the rate which the R are, are changing when the balloon is 500 feet above the ground. So, but before we dive into presenting the solution of these given examples, let us first recall that related rates problems involves two or more equations which is related to time. So we are expect to find the rate of change with respect to time. So proceed. This is our given, and then the same process since the same process from the last times. We should first at least be able to illustrate the given for us to have it be an effective or easy way of solving or finding those what is asked. So first, let us um, then, um, illustrate the balloon, which is the point A and the angle it forms. So we have the point A and the balloon, which is denotes the distance of the balloon from the ground, it's y, and the angle or the projections from the point A to the balloon is, or the line, which is r, and the ground, which is 500 feet. So, and by that we are able now to solve, since we have this illustration given, illustration given here. So denotes the angle form as theta, which is we are first we are solving here before the rate of change. So we have the variable theta as related to the equation. So we have tangent theta is equal to y over 500, since tangent or 2y is the opposite over adjacent. So the angle theta here is we have y as the opposite and the 500 feet as its adjacent line. So we have y all over 500, and by that we are able to solve for the implicit differentiations of that. So we came up with secant squared theta, the rate of change in terms of theta with respect to time is equal to 1 all over 500, um, the rate of change in terms of y with respect to time. So when y is 500 feet, theta is pi over 4, secant squared theta is the square root of 2 squared, which is equal to 2, and the dy all over dt is 140 feet per minute since it is given already in the given. So just simply substitute it to the given for us to find the value of the rate at the rate and the angle or in a point A. So we came up with this 2, since secant squared theta is equal to 2, the theta d theta or 2 multiplied to the rate of change in terms of theta all over with respect to time is equal to 1 all over 500 multiplied to 140 as the value of our dy over dt, and just do sums and just simplify. So we came up with um, d theta or the derivative of theta all over with respect to time is equal to 140 all over 1000, and then we have this final value which is 0.14 regions per minute. So the rate at which the angle at A is 0.14 regions per minute. So the next slide presents the range R are changing when the balloon is 500 feet above the ground. So we have this illustration again, the same from before, and just denotes that the range R, the variables R, Y, and Y are related by the equation R squared is equal to 500 squared plus Y squared. So just find the differentiation or apply differentiation as a process. Then we came up with 2R, the R or derivative of R with respect to time is equal to 2Y derivative of y with respect to time, or just simply this is the new formula we should apply to find the value of the rate of change in terms of y with respect to time, which is equal to y all over r multiplied to dy or the derivative of y with respect to time, when our y is equal to 500 feet, since it is the changing when the balloon is 500 feet above the ground. So we denote that y here is equal to 500 feet, and then our r, which is equal to the square root of quantity 500 squared plus 500 squared is equal to 500 square root of 2. 500 squared, since our x here or our given or the distance from the point to the base which is the balloon is 500 feet also. So we have 500 and the height which is also 500. So we came up with 500 square root of 2. And our dy all over dt is the same, which is equal to 140 feet per minute. And just plug in to the formula given, which is derivative of r with respect to time is equal to 500 all over 500 square root of 2 multiplied to 140, and simplify. So we came up with dr or the rate of change in terms of r with respect to time is equal to 140 square root of 2 all over 2, and then the final answer for that is that the rate of change in terms of r with respect to time is 70 squared feet per minute. It is r here. Proceed. So we have another example, which is a balloon in the form of a sphere is being inflated at the rate of 10 cubic meters per minute. Find the rate at which the surface area of the sphere is increasing at an instant when radius of the sphere is 3 meters. So we're looking for the surface area here from the given. So this is our given, and the same process just denotes. So we have t for time in minutes, r, which is the length in meters of the radius of the balloon at time t, the volume, which is cubic meters of the balloon at time t, the surface area of the balloon at time t, which is denoted as S, which is, this is our given here. So we have dv all over dt, or the rate of change in terms of our volume with respect to time is 10 cubic meters per minute. And our radius rather, so we have 3 meters, and we are asked to find the ds over dt, or the rate of change in terms of the surface area with respect to time. So equation, um, this given, from the given itself, we are able to relate those given into these equations, which is the formula for volume and the formula for this surface area of the volume. So we have volume 4/3 pi r squared, and for our surface area we have 4 pi r squared. Just apply differentiation, or differentiate those equations. We came up with derivative of volume, or the rate of change in terms of volume with respect to time is equal to 4 pi r squared dr all over dt, and we are asked to find the dr over dt, so it would be equal to the derivative of volume all over with respect to time all over 4 pi r squared. And the ds, or the s, the differentiation of s, or the surface area, so we came up with ds, or the derivative of surface area with respect to time, is equal to 8 pi r dr over dt, in which ds all over dt is equal to 8 pi r. Just substitute the value of dr over dt. So we came up with 8 pi r dv all over dt, or the derivative of volume with respect to time, all over 4 pi r squared. So we just combine the dr over dt to the differentiations of ds over of the surface area, the formula of the surface area. So we came up with this formula here that we are able to use in finding the derivative of the surface area with respect to time, which is 2 dv all over dt over all over r, or the radius. So we have to substitute the given, assume that this is the balloon. So we have the new formula that we can use solving for the ds and over dt. Just plug in these values. We have 2, and the dv over dt, since the derivative of volume with respect to time is 10 cubic meters per minute, so we have 10, and then our r, or radius, is equal to 3. So we have 2 multiplied by 10 all over 3, or just simply 6 points, approximately 6.67 meters squared per minute. So that will be all for today's video. I hope you keep on updating for my next video about related rates problem involving cylinder. Bye bye, and thank you.